The physical foundation of our modern computing wasn't forged in a sterile lab. It was forged in extreme, blistering heat. Inside early light bulbs, electric current pushed through a carbon filament, heating it past 2000 Kelvin. At that heat, oxygen instantly incinerates carbon, so engineers sealed the filament inside a pure vacuum. But Thomas Edison noticed a glitch. Over time, the inside of the glass bulb would turn yellow and then brown, strictly on one side. That extreme heat was physically boiling electrons right off the carbon, floating freely in the vacuum, a process called thermionic emission. These electrons were magnetically pulled toward the positive wire. Most whizzed past it, violently crashing into the glass, staining that single side. A chaotic cloud of boiling electrons holds massive potential energy, but without a physical mechanism to capture and control that energy, it remains entirely useless. In 1904, John Ambrose Fleming modified the bulb by adding a second, positively charged electrode, a metal plate designed to catch those free-floating electrons. Because the heat only came from the filament, the electrons could only flow in one direction, from the hot wire to the cold plate. It created a forced one-way street across the vacuum gap, creating a device known as a diode. Directing the flow solved one problem, but engineers still needed to control the volume of that flow. Lee DeForest solved this by placing a sparse wire mesh directly between the hot filament and the target plate. This three-electrode component became known as the triode. By applying a slight negative electrical charge to the mesh, DeForest created an invisible barrier, repelling boiling electrons back toward the filament. But a slight positive charge aggressively pulled electrons through the holes, unleashing a massive surge of current to the final plate. Engineers could now use a tiny voltage input on the wire mesh to instantly unleash a massive electrical output. They had built an amplifier that functioned perfectly with zero mechanical moving parts. By 1937, the ability to control electricity with precision met a new demand: the need to automate logic. Claude Shannon realized that binary mathematics could be mirrored perfectly by the physical opening and closing of electrical circuits. An engineer named George Stibitz put this into practice. He built the first physical binary switches by repurposing mechanical telegraph relays. Inside a relay, power to an electromagnet pulls a metal lever downward, closing the circuit to represent a mathematical 1. By wiring relays together, Stibitz forced electrons through specific pathways based on switch positions, creating physical logic gates that could literally add two numbers together. We had successfully built a physical machine that understood abstract logic. But relying entirely on heavy, physically snapping metal switches introduced a severe and unavoidable physical speed limit to our computation. The mechanical friction of metal rubbing against metal caused parts to wear down rapidly. Electromagnet coils took precious milliseconds to engage, and the thousands of physical levers slamming together created a deafening noise. To escape the limits of friction, computer scientists turned back to the glowing glass of the triode vacuum tube. Instead of using the triode gently to amplify a radio signal, they drove extreme positive or negative voltages straight to the grid. This forced the tube to act as an absolute binary switch, either entirely open or entirely closed. This meant the switch operated with zero moving metal parts. It utilized only weightless electrons, zipping silently through a completely empty vacuum at near light speed. This chain of physical logic culminated in 1945 with ENIAC, the world's first electronic, programmable computer. It required an immense scale of engineering. Humans built a towering architecture, housing 19 massive vacuum tubes, drawing city-dimming amounts of power, purely to control microscopic electrons. High-speed computation became a reality only after we learned how to force boiling electrons to perform logic inside glass bulbs. This physical mastery of invisible energy was the exact architecture required to eventually shrink those same logic gates down into modern silicon.